Okay, good morning, everyone. I hope you're all keeping well. I'll be talking about HELI antennas, even though I know most of you haven't done much with HELI antennas in the past. Our portfolio and the existing technological landscape, we're also kind of narrowing down the use cases and applications, and this means narrowing down the addressable market as well. But this is changing now. So even if you haven't done HELIs in the past, I mean, you haven't done projects with HELIs in the past, I would like you to keep your attention and stay attentive to the following minutes, where I hope to trigger you to think about the potential opportunities within your customer base. You might have some low-hanging fruit even in your contact list. We will address who these customers are, who these projects, what projects are these antennas built for. So keep an eye for it, because even though you haven't done it, you may do it in the future. So our HELI antennas, the applications for our HELI antennas are quite known of everyone. They're basically used in underground environments where the antennas make use of the walls of the tunnels as waveguides. They end up outperforming linearly polarized antennas and leaky feeders, and we're going to discuss a bit about that as well. Our customers have been using these antennas to ensure reliable connectivity systems in all sorts of mines, from coal to gold, in tunnel construction sites, and on very specific metro subway projects, amongst other use cases. Some of the most remarkable projects in Europe so far are a mining site in Iberia, where we have deployed over, where the system integrator has deployed over 2,000 HELI antennas, and the Istanbul metro, where one line is already operational and running on our antennas, where we're doing communication from the wayside, the tunnel itself, to the metro, and 3 more lines are going to be deployed and are being supplied as we speak. All in all, in our history, we have over 15,000 kilometers covered already, and we are pretty much sure this is just the beginning. Most of our HELI deployments have been done resorting to Wi-Fi frequencies, and a handful of applications also made use of LoRa or cellular frequencies. But in reality, indeed, the big majority has been done using Wi-Fi. With all the buzz around 5G and private 5G, where companies like Ericsson and Nokia are leading the way, and with public 5G rollouts being done in a good pace as well, again with Nokia, Ericsson, and other manufacturers like Huawei, 2 new opportunities will make the demand for our HELI antennas to boom. The first one is, of course, public 5G infrastructure. Up till now, cellular deployments were done using leaky feeder, which is not fit for 5G or data-first technologies. The second one is private 5G underground networks for metros and subways across the globe, or any other tunnel or underground private communications applications, where again, leaky feeder is not a fit and linearly polarized antennas are not ideal either. The increase in private and public 5G deployments, together with the antennas I'm about to present, will crack open new business opportunities for you. Before moving forward, I want to give you some technical context to back some of the claims I just made, namely that there are shortcomings when considering leaky feeder and linear antennas to deploy private and public wireless communications underground, be it 5G, LTE, or even Wi-Fi. Firstly, regarding leaky feeders. To ensure higher IP throughput, channels need to be wider. For this to happen, higher frequencies need to be used, meaning deployments using frequencies over 1 gigahertz will become more common at these frequencies. At these frequencies, leaky feeder's performance is severely impacted, as the attenuation behavior of the leaky feeder itself becomes too big. And this means that a lot of inline amplifiers are needed to keep the signal at acceptable levels. This adds to both cost and performance degradation. Also, leaky feeder offers limited and rather obsolete RF performance. There's no real MIMO when using leaky feeder, because we can't get polarization diversity, and we get, even if we run 2 leaky feeders next to each other, we almost have no spatial diversity. Moreover, because leaky feeder sends signal 360 degrees around it, it creates interference, lowering the signal to noise ratio, or in carrier terms, carrier to interference ratio. And to achieve the higher throughputs that Wi-Fi 6E or 5G or LTE make possible, we need higher signal levels and better carrier to interference ratios. From both CAPEX and OPEX perspective, leaky feeder for higher frequencies is an absolute nightmare. How many hours do we need to install 5 kilometers of leaky feeder? How much do these hours cost, including manpower, associated costs like lifting platforms or health and safety costs? How many access points or radius do we need to deploy using such approach? And by using more active radio devices, how many switch ports, how many licenses for these switches and for the radios, how many power outlet points? And so adding more elements to the solution also means servicing these amplifiers and all the associated switches and power outlets. Not only that, and this is only from the deployment and operation, what if something goes wrong, and what if someone or something damages the leaky feeder? Then it takes longer to repair, there are longer service outages, and there's a higher cost, of course, to repair the infrastructure. Finally, leaky feeder is, of course, not as flexible, not as scalable as an antenna-based underground communication. Because with antennas, you can deploy the antenna, and as the tunnel increases, if you're still constructing or you're still building the tunnel, as the tunnel grows, you don't need to keep on running the leaky feeder. And this means antennas are actually easier to both to scale up and to scale down quickly to accommodate to changes, not only in the construction time of the tunnel, but also once it is in operation. With regards to the comparison between circularly polarized antennas and leaky feeder, and with circularly and linearly polarized antennas, there are also shortcomings when considering linearly polarized antennas. The first thing is, of course, linear polarization rotates unpredictably down a tunnel. This means there can be little to no signal for linear antennas on the end user device, laptop, smartphone, tablet, whatever, at certain point of the tunnel. HELI antennas, on the other end, they contain all polarizations, therefore resulting in significantly more reliable connections. Linear polarization propagation varies greatly depending on tunnel dimensions and surfaces, and circular adapts better because it has all the polarization. So what I mean is, when we're sending a linear polarized signal down the tunnel, it will bounce and be reflected and attenuated, absolutely unpredictable. So there may be tunnels where at a given point, or for that given tunnel, I have a better reception with vertically polarized when the signal is being transmitted with a vertically polarized antenna, and other tunnels where I get better reception if it's being transmitted with horizontal polarization. If I have a circularly polarized antenna transmitting the signals, I have all the polarizations there, so I will be sure to better adapt to whatever tunnel. I don't need to think, and I don't need to test how the tunnel will perform for horizontal or for vertical polarized antennas. A bit on the same note, circular polarization propagates past obstacles and obstructions more reliably. Basically the same. Some polarizations at a given moment in time, and depending on the obstacles they face, train, cars, trucks, machines, they are going to block a given polarization, or they're going to attenuate it. When we talk about circularly polarized radio waves coming out of a circularly polarized antenna, this doesn't happen as much because, again, we have all the polarizations there. Then if we think about resilience and reliability, of course, and that's what it all comes down to, we can then add to the reliability of the system that's brought by circularly polarized antennas, antenna diversity techniques, both polarization and spatial diversity. Basically, if we use two circularly polarized antennas, one would be right-handed circular and the other one a left-hand circular, and we've spaced them at least by one wavelength apart, ideally 3, as you know, we make sure that we get the full benefit of MIMO, both in terms of throughput. So this means that we can actually multiply the throughput from traditional systems, but also in terms of signal reliabilities, in the way that by having spatial diversity, and indeed having spatial diversity, we will be fighting fading and improving the radio links capacity. Anyway, all in all, this will lead to, if you're deploying a wireless communication system underground using circularly polarized antennas, you will need less access points, less radios, or if you keep to the same number of access points and radios, you will create a system which is much more reliable, where throughputs are higher, latencies are lower, connection dropouts are lower as well. But these arguments need to be fine-tuned depending on who you're selling these to. I will address that later on.